by the end of lecture today, you'll be able to apply the ideal gas equation of state in solving engineering problems, and also you'll be able to understand real gas behavior and apply the compressibility factor. So we can only use ideal gas equation of state for ideal gases, and you'll be introduced to compressibility factor so that you can try to use a similar equation with compressibility factor to represent the behavior of real gases. And also you'll be able to calculate the internal energy by using thermodynamic tables. We learned a lot of properties, pressure, temperature, and specific volume already, and now we'll introduce ourselves to internal energy. So if you want further readings on this matter, like these are the reading list that you see on the right. Okay. All right. So let's look into today's content. And if we go back to our previous lecture, you remember we learned the ideal gas equation, which is PV equals RT. P is the absolute pressure, V is the specific volume, R is the gas constant, and temperature, most importantly in Kelvin, the temperature in Kelvin. So you remember, we agreed that the ideal gas equation can only be used at certain instances, either when the pressure is very low or either the temperature is very high, or both, right? So in these instances, we can use ideal gas equation usually, but sometimes these conditions are not met by our substances that we are dealing with. In such a situation, we use compressibility factor in this equation to represent the deviation from the ideal gas behavior, right? So a real gas is not exactly behaving as an ideal gas. So this compressibility factor that we have here, we use it as a correction factor. So the compressibility factor is a function of pressure and temperature. Okay. Now let's look into further in this compressibility factor. What you see here is the compressibility factor against the pressure. Give me 1 second. Against the pressure. So this is for one substance only, like this chart is given for nitrogen. Okay, so let's try to see what are the important information that we can derive from this one. If you look closely, you can agree with me that we don't need this section of the graph for our gas evaluations, right? Because the blue color section is not exactly only gas. It has liquid plus vapor. So we are not going to apply any gas equation into any liquid, no matter what, ideal, real, or whatsoever. To any liquid, we are not going to apply gas equations. It makes sense. The name says gas, right? So we are not going to do that. We are trying to see whether how we can use our ideal gas equation or real gas equations outside this dome. Now, outside the dome, you see that there are some isothermal lines drawn, 130K, 150, 200, and 300 Kelvin, right? And when you are moving this direction of the arrow that I just drew, what can you see? Is there any speciality? Like we have Z equals 1 here, Z equals 1 here. So once we are moving in the direction of the arrow that I just noted, is there any specific thing or special characteristics that you see? Perfect. So it becomes very close to Z equals 1, and at the same time, especially if you look at 300 kelvins, you can see irrespective of the pressure, now even with increase in pressure, like up to this range, it is Z equals 1, right? So when we see that Z is equal to 1, in a physical sense or in a practical sense, what we can say about this gas's behavior? Does it reflect the behavior of gas by any means? Like whether it's ideal or real? Yes, like becomes very close to ideal behavior, right? So PV equals ZRT, right? So when Z becomes 1, what happens is our equation turned into PV equals RT, right? So you can see when we have PV equals RT, this is ideal gas equation, right? So a real gas become close to ideal behavior when the temperature increases. This is something we agreed in the last lecture. And you can see from this chart that it is going to happen, right? And another important note that I want to highlight here, the other important thing I want to highlight here, once the pressure is reducing, see what's happening. When we go along the x-axis towards the left, then we see that all the isothermal lines converge towards z equals 1, right? Like every line comes closer to z equals 1. So this validates our other agreement that we had during the last lecture. When the pressure is lower, the gases behave closer to ideal. Okay. And there was another thing that we had when we are deviating from the critical temperature, or we are exceeding critical temperature significantly enough, then we get closer and closer to ideal gas behavior. Now, with this one, we can see how we can calculate the compressibility factor. Like if you want to calculate the compressibility factor for nitrogen at a given point, then simply what you do is you pick your pressure. Let's say it's 4 kilopascals, and if it is 300 Kelvin, so you just go up here and find the place where you cut the isothermal line, and then you go along this line and find your compressibility factor. But can we use this graph to find the compressibility factor of oxygen or methane or nitrogen or something else? We cannot, right? Because this is developed for nitrogen. This is not generic, right? So it's like different gases have different characteristics. So we cannot use one characteristic from graph from another gas to interpret the other. So what are we going to do about it? So in order to address this issue, we develop generalized compressibility chart, right? So we can use generalized compressibility chart to find the compressibility factor of different gases. And here there's a catch. If we just consider the pressure, then it's going to be different. The impact of pressure, what is high for a given gas is subjective. What is a higher temperature for a given gas? We compare our temperature to the critical temperature, and then only we can say this is a higher temperature compared to the critical temperature. Therefore, this gas will be close to ideal behavior, right? So we cannot just look at, let's say, we look at 175 Kelvin and say that it's very high. We cannot say that, because for a certain gas, the critical temperature may be 180 Kelvin. So in that case, the higher temperature would be like around 300 Kelvin, 250 Kelvin something, right? So it's similar to us. Like let's say if I take my body mass or weight, then whether it's higher or whether it's in the lower side, it is subjective. Like then you have to ask another question: what is your height, right? And then after looking at the height and weight, you can calculate the body mass index and say, okay, now when we look at the body mass index, we can say, okay, this person is in the right weight or over the weight or less than the weight, right? So similar to that, to bring everything into context, we define two new parameters. So for pressure, we define something called reduced pressure. Like it's not pressure reducing, it's called reduced pressure. Like it's just the way they named it. I would have named it in a different manner because this is confusing in a physical context like this. Then when we are dealing with gases, we call it reduced pressure. Somebody may say, okay, reduced pressure, like what's that? And so, however, pressure divided by critical pressure is called the reduced pressure. Let's say our pressure of interest is 10 megapascal, and then the critical pressure of the given substance is 20. Then our reduced pressure is going to be 10 divided by 20, which is going to be 0.5, right? Similar to this, we can calculate reduced temperature. Reduced temperature is temperature divided by critical temperature. Now, this temperature is given in Kelvin. If you substitute in Celsius, then it's going to be a problem. Then it will not work because this relationship is designed based on Kelvin scale, right? So in order to be safe during this course, if I want to get a temperature ratio, if I want to substitute temperature in an equation, I would try to use Kelvin just to be safe, right? If I do not remember what to use, Kelvin or Celsius, I will then use Kelvin. That will make my life safer. And at the same time, it's important to note, even though we use Kelvin in all equations, the tables are given in Celsius. So the unit conversion is inevitable. You should know how to convert Celsius from Celsius and Kelvin, between Celsius and Kelvin. So T Kelvin is equal to TC plus 273.15, right? So if you have the Celsius reading, this is how you do it. I'm pretty sure most of you remember how you do it. Okay, now that's done. Any questions regarding how we calculate the critical pressure and critical temperature? Or are we all good? Perfect. So now let's say for a given gas, we calculate our reduced pressure as 2, right? And now our critical temperature, our reduced temperature is 1.2, let's say, right? So in such a situation, we need to find our compressibility factor. Now our reduced pressure was selected to be 2, and then we say that our reduced temperature is 1.2, and then we go up here, find the intersection, and then we go towards the y-axis to find that coordinate, right? Now you see that this is going to be our compressibility factor. Why did we pick the third line? Okay, that's a very good question. So reduced pressure is given in x-axis, right? So but for reduced temperature, we don't have any axis, but we have, I would say, iso reduced temperature lines, right? Like constant reduced temperature lines are drawn here, like you see TR equals 1, TR equals 1.1, 1.2, likewise. So our interested TR value was 1.2. That's why we picked the third line that we see here. Did I answer your question, Menda? Oh, why did we have 1.2? That was just a question, like the question, right? So let's say in an actual question, what you would have is your temperature is, let's say, I don't know, 320 Kelvin, right? And pressure is 4 megapascals, right? And then what you would do is, like, you will, based on these, you substitute your temperature reading in your reduced temperature equation and find the reduced temperature, and you pick your pressure reading and you plug it into your reduced pressure equation. And to find these critical pressures, depending on the substance, you can find it on the property tables, right? you go to property tables. Like if we quickly go to property tables here, and then what I will do it, I will search critical, because I need to see critical constants, and I will be led to this table, and depending on the substance, I can find, okay, this is my critical pressure, critical volume, and critical temperature. So I will pick these numbers if my interest was in fluorine, let's say, and then I'll pick it here and then use it in my equations to cater for P critical and T critical. And after calculating the critical reduced temperature and reduced pressure, I will bring that up to this table and then do the procedure I just did. Is it clear now? Awesome. So in addition to like the process of calculating the or determining the compressibility factor, it's very important to note that there are many gases, multiple gases that is shown in this graph, right? So it's not only one substance. This graph was developed considering methane, ethylene, ethane, propane, and everything. So different symbols that you see here represent a different substance. And when we look at these lines, you can see that all the symbols fall on these lines very nicely. So you can see that this relationship is not only valid for one substance or one gas, it is valid for multiple gases. So that's why we can use this as a generalized framework or generalized figure to find the compressibility factor, right? So let's move on. Now, Lee-Kelser simple fluid compressibility factor, right? We can use this to determine the compressibility factor, and this graph will be what you are dealing with in your exams, right? So if you go to a canvas and under important documents, you will see compressibility factor, then you can download that PDF and then use it in your exams, right? So I anyway suggest you to download all the tables and content in important document folder before your exam, so that you have it in one place. You can either go to the canvas and check it, or you can just download it and keep it in your computer so that you have it handy for your questions. And exam is not closed book, it's open book. You cannot use your mobile phone or other any communication media to communicate to your friends, family, or whatsoever during the exam, but you can use internet or anything. It's fine. Okay, perfect. So this graph is very similar to what we had during the previous slide. So it has like ISO reduced temperature lines, and the x-axis is reduced pressure. So similar to what we did last time, you can, if you know the reduced pressure, you go there, and if you know the reduced temperature to be this value, let's pick, and then you go there and then you find the compressibility factor from the y-axis. Okay, so any questions so far, or are you all comfortable with finding the compressibility factor for a given gas once the pressure and temperature is given? Okay, perfect. How can we know which graph to use? You will not be dealing with multiple graphs. This is the graph that you use. This is the one you have in the canvas. So this one was to explain the process. So you can stick to this one. Okay. Why this chart include liquid as well? So any substance has a liquid, right? So we cannot use the compressibility factor for this section. We do not worry about that, and we just use the sections that belongs to gas or vapor. Okay, because we cannot just avoid the dome, right? So we can just delete it, like, but it doesn't make sense. It's just a property of the substance, right? So it's the state of the substance. It just stays there. Okay. Now, as you all are comfortable with tables equation of state and compressibility factor, let's dive into the problem right now and see whether you can find the specific volume of water vapor at 10 megapascal and 600 Celsius by using superheated water vapor table and ideal gas equation of state and compressibility factor. Like now you are going to find the same property using three ways that we identified: the property tables, ideal gas equation of state, and also the compressibility factor. So we can see what are the best ways to do this. Okay, take about 5 minutes and try to solve this question. Okay, so now in this question it says compare the specific volume of water vapor at 10 megapascal 600 Celsius by using superheated water vapor tables. So when it clearly says it's superheated water vapor table, then we can just look into superheated water vapor tables. We don't have to decide, okay, this has whether this has some bit of water or not and everything. So we have it clearly directed into this superheated water vapor table. So we can just go on and look into that, right? 1 second. So now if you go into superheated vapor tables, what you should be doing is you should be locating your pressure first, right? So pressure 10 megapascals. So now you need to find your 10 megapascal pressure, right? And then there we have 10,000 kilopascals, right? So please be aware of the units that we use, because in the question if you see megapascals in the table, sometimes you may not see the exact same thing as we had right now, right? We only had kilopascals. So instead of looking for 10 kilopascals, we have to look for 10,000 kilopascals, right? After locating your pressure range, what you would do is you would locate your temperature value and then uh, go there and find your property specific volume, right? And it's very important to note that there's a portion of this property table that is blacked out by mine, right? So I just omitted this part. So what is this portion? So it is the properties at 8,000 kilopascal, right? So in the actual case, let's go real quick to our property tables. I will type superheat and then superheated water vapor, right? So what we are doing is now in this scenario, give me 1 second. In this scenario, what we are trying to do is to find 10,000 megapascal, 10,000 kilopascal, right? So this is an easy trick, you see. So you have 10 kilopascals. Don't fall for that trap. So keep browsing and until you find the right value. 10,000 kilopascals, right? Okay, so we have 10,000 here, right? In 10,000 here, and our temperature is 600, and we go past 8,000 mark because we don't want the properties for 8,000, and from here onwards we see the properties for our interested state. Are we all clear about that one? Any issues so far? Okay, perfect. So now from that we found our specific volume, which is right here, nice and beautiful. So we call it 0.03837 cubic meters per kilogram, right? And then we can use our ideal gas equation to calculate this specific volume. So it's straightforward. So in this case, the substance is water, right? So there, what you can do is you can go to your property tables. If you don't know the gas constants, so for ideal gas, you type ideal. So ideal gas properties at this temperature. Now you browse through until you find water, right? And we don't find water. Now what? We don't know. We don't know the ideal gas constant, right? So now what can we do? So we are stuck, right? But wait, we have a solution for that. I would search water and then come here. Sorry, if I zoom out this a bit. So in the critical constant table, we have something which can save us. So if I go here, and then if I look here, we have the molecular mass, right? 18.015. So molecular mass, you know that if we don't know the gas constant, we can use this, right? So our gas constant is essentially Ru divided by molecular mass, right? You remember we discussed this one during the last lecture. Therefore, it doesn't matter if we have the gas constant, if we at least know the molecular mass, still we can find the gas constant, even though it's not given in the property tables. So we pick molecular mass to be 18 grams per mole. So we now go back into our question, and there what we can do is, instead of using PV equals RT, we can use PV equals RU into T divided by molecular mass. Anybody having challenges understanding this equation? Sorry, wasn't there something in last lecture about not using the ideal gas equation for water vapor? That is very true, Kylie. Like, we are not going to use ideal gas equation for water vapor or water anything during this course, except like it is asking us to do so. Like this question asks us to use these three methods to calculate so that we can compare. This is just for comparison. Yeah, like no, like the thing is, like water is significantly deviant from the ideal gas behavior. That's why we are not using that. And at the same time, on another note, we have property tables for water, a comprehensive set of property tables for water. So whenever we have the property tables, we are not using ideal gas equation to use that for that substance, right? So in the case of water, we are not going to use this. This is just for demonstration, like to compare the values, okay? Perfect. So anybody having challenge in understanding this equation? Okay, so I see none. So we plug the values. So universal gas constant, so 8.314 joules per mole per Kelvin. And then our temperature, most importantly, 873.15 Kelvin, right? So what we did is we got our Celsius reading and converted it to Kelvin, right? TK is equal to 600 plus 273.15, right? So this is what we did, and now we have this value here, and then in addition to that we have our pressure values. So the pressure value 10 into the power 7 pascals, right? You see that we do not substitute kilo or mega unless you know that some kilos in the top are going to be cancelled out with the bottom. If you are not sure what that is, just substitute everything with the standard units, right? Now, not without kilo or mega or something like that. Standard unit in the sense of mass is kilograms, though it's not grams, right? That is the only exception that I see. So the pressure in pascals and molecular mass in kilograms, 18 grams per mole. So we converted it to kilograms, 0.018 kilograms per mole. So we are here with the final answer for specific volume, which is 0.04, right? What we had 0.40, and what we got from the property tables was 0.038, right? Are you all with me there up to this point? Any confusions? Guys, let's be interactive in the chat. That makes it easier for us to move forward with the lecture. Perfect. Otherwise, I don't understand what you are thinking, whether it's challenging for you or whether it's too easy or whatsoever, right? So sorry, how did you get the formula PV to V2? So what we usually see in this course is PV equals RT, right? So but the gas constant is Ru, the universal gas constant, divided by the molecular mass. So we substitute for R, and then we get PV equals Ru, sorry, PV equals Ru into temperature divided by molecular mass. Did I answer your question? Yes. So the as a rule of thumb, like what we would do is we would first look for the property tables, because that is the most accurate, because it is developed based on experimental data, right? So it is the most accurate, and when we do not have the property tables, or when there's no significant accuracy compromise uh, when using the ideal gas equation compared to using property tables, these two instances we are going to use ideal gas equation, right? So the accuracy and everything, it all depends on the context, right? So you remember that we discussed like the decision making in city level, like we think people as a whole and we look into the lower level resolution, and sometimes the accuracy that we are trying to achieve in certain processes are not significant enough to go through that trouble. So in such situations we go for simplifications. So to summarize what I just said, if we have property tables, it's always a good idea to go for the property tables first, right? And then if we do not have property tables, then we can look into the ideal gas equation or the gas equation modified for real gases using the compressibility factor. Did I answer you, Dami? Right. So now the last one, compressibility factor. So how can we find the specific volume of this given substance using the compressibility factor, right? And here the compressibility factor, to find the compressibility factor, we need to find the reduced pressure and reduced temperature. In order to do that, we have to find T critical and T critical. So similar to what I did, if I go real quick to my property tables, so I will go to critical constants that I see here, right? And there you see that the critical temperature and critical pressure is given, right? So for water, critical temperature is 647 Kelvin, and for water, critical pressure is 22.12, right? So I pick these values, and then I come back here. So I have the critical constants, right? And then after having those two, what I do is I calculate the reduced temperature and reduced pressure. To calculate the reduced temperature, it's very important. I cannot emphasize this enough. Always use Kelvin, right? If you use Celsius, then your answers will be wrong, and for no reason, because you knew how to calculate the reduced temperature and still you could not score the marks, right? That is pity. So 600 plus 273.15, so divided by the critical temperature, we come across 1.35. as our reduced temperature. And then to find the reduced pressure, 10 megapascals were our pressure and critical pressure was 20. So 20.12, 22.12, and then we come across 0.45 reduced pressure, right? And then we go across here in this table and we try to locate our reduced pressure, right? The slightly taller tick marks are like 0.1, 0.2, 0.3, 0.4, and 0.5. And in the middle, the relatively smaller tick marks are going to be 0.5 scale, like 1.15, 0.25 kind of things, right? So similarly, we locate 0.45. And then we, oops, this is not vertical. This is supposed to be vertical. I'm sorry. Okay, that is good enough, I guess. Okay, now after locating that, like when you are doing this, like don't do this. You see that I draw this using Paint 3D, like just put a box. That is the easy way. Like whenever I have an image and like I need to grab a quick reading, like accuracy doesn't matter too much, then I go for 3D, Paint 3D, and like just draw a box, right? So there, now we need to locate our reduced temperature, right? When we look at the look at the figure here, let me zoom it for you. Now you can see we have 1.3 and 1.5. Our reduced pressure reading was 1.35, but at this point I just picked 1.3 because from 1.3 to 1.5, like there's this small gap here. So if you are very keen on making it further accurate, you can try to do some linear interpolation and divide this into 4 sections, this line section into 4, and then get your line like this. Or in this situation, I would round it up to the first decimal point, and then from the first decimal point I can go to the compressibility factor. And here you can see that it is somewhere between 0.95, this is 0.95, and this is 0.9, right? So 0.9, 0.95, and 1. Like these are the numbers that we have. So I would assume this to be 0.93 or 0.925, something like that, because this is in the middle of the thing, right? Now, from that, I get my compressibility factor to be 0.93, and then we plug everything. So we can say that V3 is equal to Z into RUT over Pm. M is the molecular mass, P is the pressure, right? And this portion we already calculated because RUT into P over PM, RUT over PM is essentially V2, right? So basically we can say that this is equal to ZV2, and we plug in the numbers and we get this result, right? Anybody having issues with how we calculated V3, or are we all good? Is it very clear? Perfect. So now if we check this one, you can see that V1 0.038, we had V1 as 0.038, right? Cubic meters per, sorry, cubic meters per kilogram. And then V2 was 0.040, V2 0.040, right? The same unit. I'm not going to write it down here, but now you can see that V1 is closer to V3, right? So, or rather V3 is closer to V1. V1 is the property tables. This is from tables, and the value that we calculated using considering the compressibility factor is very close to what we got in our from our property tables, right? And the value that we got using the ideal gas equation is relatively further away from the property table values. So now with this one, we can see that property tables is always the place to go if we have it, or unless it's specified to do otherwise. And compressibility factor is the other model that we can calculate for better accuracy. So that will be our second choice. And the ideal gas equation is our last resort unless specified, right? Okay, any questions so far? Okay, all right. Now, yeah, there's a go ahead. Go ahead. No, like, can we solve a problem using a combination of both tables and equation state of state, or is it? No. So we don't do that. We don't even mix two tables. I mean, not two tables means like the table set I have given, that is one table set, right? So we don't use that table set with another table set from another reference. So because I will tell you why in a little while, but at the same time, like, we don't even mix up two table sets with each other, and we don't want to mix equation of state and tables, and no, we are not going to do that. Okay, all right, let's all take a 4-minute break before we move into the next section, and then we'll introduce ourselves to the concept of internal energy and the other components that we have to learn today. Hello everyone, are we all back again? So now let's move into today's discussion, and it's a very important topic. So, forms of energy, right? You know that we are in an energy crisis and we are trying to improve the energy efficiency. Even my PhD is focused on improving the energy efficiency of building, right? So we talk about energy a lot, and but still, what is this energy? What is this so-called energy, right? That we all want to save and we want to, like, whatnot, do everything, right? So what is this energy? So it's I try to find an exact definition for this one, but like it says it's very hard to define, but people would like to interpret, like, this is not a definition, but like to interpret it as a property that enables or us to do work or transfer heat, right? If we, for an example, what is energy? Like, if we have more energy, then we feel like playing, running, or singing, or whatsoever, like that, whatever the things that we like to do. And if we are low on energy, like, then we cannot do work, right? So similarly, you can remember energy as a property that enables doing work or enables transferring heat or something, right? And you know that you expose yourselves to these two forms that you see in the screen in the previous classes or in your high school, right? Kinetic energy. And kinetic energy is associated with motion of a system. If you are going on your car at 100 kilometers per hour, then your car has a certain level of kinetic energy. And what is that? What is the amount of kinetic energy you have? It can be determined from this one, right? This equation. So kinetic energy is 1 over 2 into the mass of the substance or mass of the system that we are talking about. So in the example of your car, it's going to be your car, mass of your car, right? Maybe 1500 kilograms, and V is going to be the speed of your car again. So it's going to be 100 kilometers per hour. So if we substitute these numbers, we'll get a kinetic energy value. So if you substitute kilometers, then you will not get the uh, energy in joules as we expect. So if you want to find everything in standard SI units, you have to substitute that in meters per second, right? And similarly, the potential energy is given to you by the elevation of a system due to the gravitational field, right? So this is another mechanical energy form. And if you are at a 10 meter high position, so that is going to be your mass into gravitational acceleration into the height, that 10 that you are 10 meters that you are up, right? So once, if you have this rock that you see in the slide falling down, your potential energy can be converted into kinetic energy. Okay, this is the stuff that you already know, very clear, right? And when we look into this potential energy thing, this gives you a very important understanding. So what is this Z? To, like, this is the height from a given point. How do we pick this given point? Any idea? Okay, so to find the reference, let's say in my example I said 10 meters, right? I pick my reference to be the word water surface, and then this is my Z, 10 meters Z, right? So this is, like, I picked the water surface. I agreed that I consider the water surface to be the zero potential level, right? If I have something underneath the water surface, that is going to have a negative potential, right? Because it's going to be minus. So you can see this is something we agreed upon, and somebody else like this, I would solve this question considering this reference, and somebody would solve this question using this as the reference, reference 1, reference 2. So would that create an error if somebody pick the top of the mountain or the cliff is the reference for our potential energy calculations? Would that be erroneous? Would that be a problem? Would that be a problem? Yes, no, not sure. What would be your answers? Okay, so we have one answer, not sure, but maybe yes. Okay, so any other answers? Okay, I will answer that question then. So the reference point does not really matter, because what we are interested in energy analysis is the difference of energy. So if we pick this one as our reference point, then it is, our potential energy will be zero. But once we go down here, our potential energy will be mg into minus 10, right? Oh, my pen is giving me a hard time today. Minus 10. Okay, let me clean up the screen a bit before going with the explanation. So this is our reference 1, is our reference 2, right? So the height is 10. So when we want to find delta PE, to evaluate how much potential energy is converted from PE to KE during this fall, what we want to do is we want to get PE1 minus PE2. Do you agree with this one? Potential energy we had at the first point and minus potential energy we had at the second point, right? So if we start with our original reference, the water surface, PE1 is going to be mgh. mg into 10, right? And PE2 is going to be 0. So we'll call this one delta PE1 is equal to mg into 10. Agreed? Anybody having doubts about that? Okay, so now let's call delta PEA, like we'll call it scenario A, otherwise PE1 and PE2, everything is going to mix up. Now we'll consider this second reference, right? So we'll call the potential energy difference occurs at that point as delta PEB equals, at this point now we consider this as PE0 level, so 0 minus mg into minus 10. Agreed? Because at this point it's going to be minus 10 now, because we considered the top of the cliff to be our zero potential level, right? So you can see in either case the potential energy difference is going to be mg into 10. Do you see that? Perfect. So now you see that the reference is just an agreement, but it doesn't really affect the final answer, right? So the important thing that you have to note is it doesn't really affect the final answer until you keep the same reference throughout the calculation, right? If you start with PE0 here and then after 5 minutes you decide, okay, now for the rest of the calculation I pick this as my reference. No, you cannot keep on changing the reference like during your calculation. So if you agreed upon something, you have to stick to that and then do the calculation following the same agreement. Okay, so do we have this reference in our kinetic energy calculations? Is it relative to something? Like, do we also calculate it relative to something? Now we agree that we calculate the potential energy relative to a pre-agreed zero potential level, right, or reference level. So do we have a reference like that for kinetic energy? One answer is no. And anybody else? Okay, so I will make it further uh, clarified. So is this velocity, is it calculated or is it presented relative to something, or is it like kind of absolute velocity or something? So like when you say you are going on 100 kilometers per hour, going at 100 kilometers per hour, right? So then is it relative to something, or like is it like absolute speed or absolute velocity? It is relative to what? It is relative to what? Oh, you were so close, Alexandra. Like, it's sad that you had to uh, roll out your argument. So, anyways, you were close. So, the thing is, it is relative. That's the correct answer. The thing is, we calculate not exactly, it could be relative to the viewers, but in this case, like when we say that our vehicle is going at 100 kilometers per hour, we say that it's relative to Earth, right? We give that speed relative to Earth. Like we assume our Earth is stationary or our road is stationary, and then to that, with respect to that, we give our speed. But in reality, our world is also rotating, right? Our world is also rotating. Somebody in the Mars would look at us and say, okay, this guy is going at 120. He's really breaking the speed limits. But we are really going at 100 because he's seeing the velocity of Earth plus our velocity, right? So maybe some guy in the Mars have better work to do. But in case, see, now you get the idea, right? Are we all clear? Okay, so anyways, what I wanted to emphasize is every parameter, most of the parameters we calculate with respect to some state, right? Some agreed reference. So now let's jump into internal energy. So internal energy, the definition says the sum of all microscopic energy related to the molecular structure and molecular motion of a system. Okay, so we'll look into our favorite coffee cup here. Yeah, it's not exactly a coffee cup, but let's say it's a coffee cup. Oh, it looks like a coffee cup. So now, if we keep on stirring this one for about maybe 2 hours, like very fast, like then, and all of a sudden we stop that and we stay calm. And now, would this cup be moving everywhere? Would this cup move somewhere? No, right? And then if the cup does not move somewhere, then what can we say about the potential energy? It stays the same. What can we say about the kinetic energy of the total system? It stays the same. The water surface will stay the same. But the particles inside this coffee, like inside the coffee liquid, right? So those will be rotating and moving here and there. We might not be able to see the water, the coffee surface would look calm and quiet, but inside that there's a lot happening. These molecules are going everywhere and like colliding with each other, and there are chemical bondings attracting each other. So how do we represent that? We cannot use potential energy and kinetic energy or either of those to represent that aspect. To represent this microscopic energy related to the molecular structure and molecular motion of a system, we use internal energy, right? So for ideal gases, the internal energy is a function of temperature. So if the temperature goes higher, then internal energy level goes higher. If the temperature goes lower, then the internal energy level goes lower, right? So for ideal gases, for other gases, let's say for real substances, the internal energy is a property of temperature, and there could be other parameters such as pressure that is determine the internal energy level, right? And it is very important to note that internal energy is an extensive property. What does that mean? So it means internal energy depends on the mass. Let's say we pick this coffee cup and then we take another cup and we pour half of the cup into the other one. Now each cup has same coffee level, right? So what can you say about the internal energy level in both cups? In one cup, we have half of the internal energy we originally had in the first cup. Did I make sense there up to this point? Do we have any reservations? Anything not clear? Perfect. Now, now this is a PV diagram. Okay, the missing here, P was missing here. Now, so this is a PV diagram, and in this PV diagram, we go in different paths from 1 to 2, from A using A, B, and C. So when we go from 1 to 2, after reach state 2, does the path matter? I mean, let's say we heat something to reach state 2. Let's assume, right? We do work some way, and then we reach state 2. There we use path A, and then we did something else to achieve the same thing using path B. Depending on the path, would the temperature at state 2 change? I need quick answers. No, it doesn't change, right? So Depending on the path, would the pressure of that state change? No, right? Same goes for the specific volume, right? It would not change because we are at state 2. And what about the internal energy? Would that change? It changes, but specific internal energy does not change. Specific internal energy does not change. That given state, specific internal energy does not change, right? So specific internal energy is a property. It depends on temperature. We agree, right? Temperature and pressure sometimes. So if it is dependent on temperature and pressure, so it does not depend on the path. Do I make sense? Right? Once we arrive at state 2, the specific energy does not depend on the path. It's state 2. It's like this: you can use a highway, you can use a downhill drive, or you can use some other roads to reach UBCO. Once you reach UBCO, it's UBCO. Like, not depending on the highway you used, EM is not going to be a different place. It's going to be the same thing no matter what, right? So it's an important notion. Change in state properties are independent of the processes, right? And there was another thing: extensive property. Internal energy is an extensive property. How about specific internal energy? Specific internal energy means internal energy per unit mass. What can you say about that? It is intensive property. It is an intensive property because it does not change, right? So we had full cup. We have had, let's say, 10 kilojoules for the entire cup, and let's say this is 2 kilograms of coffee. That's a big coffee cup. And now the total internal energy is 10 kilojoules, and specific internal energy is going to be 5 kilojoules per kilogram, right? This second parameter does not change even if we pour half of the cup into another cup. So like, even if we had 2 containers, 1 kilogram of the coffee would have 5 kilojoules of internal energy, right? So therefore it is an intensive property. Sorry. Okay, now let's go on here. Now we learned something new today. In addition to kinetic energy and potential energy, we have internal energy, right? So when we try to analyze the thermodynamic system, we have kinetic energy. If the system is moving, then if the coffee cup was inside a car, then it would have kinetic energy, right? And the car is climbing a hill, so it have certain amount of potential energy, and there's a potential to change, right? And then at this given point, the coffee has certain temperature and pressure, so that's going to be your internal energy. So there are 3 energy values that we have to consider in our thermodynamic analysis. If there's a fluid flow involved, this equation will go further. So we are not going to discuss what happens when a fluid is flowing, right? A substance is flowing. But at this point, if we have a coffee cup or some container containing a certain substance, we can use this equation to represent the energy of the system. And then if we divide the entire equation by mass and take this out, then inside the bracket we have specific internal energy, specific kinetic energy, and specific potential energy, right? So what does this mean? So like it would be good to see this one. So specific internal energy and specific kinetic energy will be, oops, half V squared plus GH. This is going to be your specific form inside the bracket, and outside the bracket you have the mass, right? For a system free of magnetic, electric, and surface tension effects, the total energy of the system is the sum of internal energy, kinetic energy, and potential energy, right? So it's important to note the SI units for energies in joules, and the SI unit for specific internal energy is in joules per kilogram, right? Anything not clear up to this point, or everything going good? Perfect. So now we are trying to calculate internal energy, right? You remember I emphasized that all the time we use, many times we use a reference point to calculate the energy levels, right? So similarly for internal energy also we consider a reference point. So the first statement says UHS cannot be measured directly, right? And they are calculated with respect to a chosen reference state. So H and S, forget for now, like forget about that. We have not discussed yet. So anyways, all three parameters cannot be measured directly. So you cannot just hold a meter or something and say, okay, this is the internal energy. No, you cannot do that. Similar to the speed or something, like we use a reference point and compare to that how much internal energy do we have, right? So this reference is usually the triple point. This is why I said to you earlier that don't mix up two property tables. If the reference point of one property table is not the same as the other property table, like property table sets, right? So this set you can use compressed liquid table and saturated liquid table and get the values from both tables and use that in combination. That's a different story. You can do that, but don't mix up this table set with another table set and go back and forth. Stick to one reference when you are trying to determine the properties. This brings up another one. So when you go online, there are property calculators, right? So in your exam, don't use the property calculators because it is not the ones that were used during the marking scheme preparation. So what I provided you is the ones that we use in marking scheme. Therefore, stick to the ones that is in the canvas. Okay. And then for the reference state for water is saturated liquid at 0.01 Celsius, and internal energy there is 0, enthalpy is 0, entropy is 0. Similarly, for ammonia, saturated liquid at minus 40 Celsius, so HF, UF, SF, everything is going to be 0, right? So at the reference state, we consider this value to be 0. It's similar to what we did with the potential energy, right? So the whatever the reference state we pick, we make it 0, and then we do our calculation from there onwards, right? So so similar to potential energy in thermodynamics, what we are interested in is the changes in U, H, and S. The absolute values of U, H, and S, that is not something we are very keen on. Like what we try to do is, what we try to do here is we try to use work and heat to do something useful, right? So thermodynamics is about using thermal energy to do something useful. So when we are trying to do something useful, we are not so worried about the individual states, what would be the absolute internal energy. We have to calculate that in the questions, but like what we are trying to find is the difference of internal energy in two states, right? Okay, so the last point reiterates what I said. To be consistent, use the set of tables from the same source for your calculations. Okay, are we all good there? Perfect. So now you can see for single phase states, compressed liquid water and superheated vapor water, like you can, if you go to the same property tables that we use to find the specific volume, you will see this new friendly parameter now, because now we know it, right? So internal energy is everywhere now. So we have our good old friend specific volume right beside it, and then in addition to that we have internal energy, right? So there we can use the property tables to calculate the internal energy similar to what we did with specific volume, right? Nothing different. So like when you go to saturated water vapor tables, there you will have pressure entry and temperature entry again, and similar to what you did in finding the specific volume, you can try and find the internal energy, right? So you remember for two-phase region, we can write our specific volume using this equation, right? So specific volume is equal to Vf, which is the specific volume on the saturated liquid line at that given pressure temperature values, and then Vfg. Vfg is this space, right? This distance. You have the Vfg's equation here, right? Similar to this one, you can use this equation to calculate U equals UF plus XUFG. So basically that says, if we draw the TV diagram, we have something like UF, and then we have something like UG, not something like, we have UG, and then this distance is called UFG. What you did with quality to find the specific volume, you can do the same thing for internal energy. When you expose yourselves into enthalpy, entropy, and other parameters like that, then you will see you can use the same relationship. Like if you had enthalpy here, you will have HF and HFG, right? And if you had specific volume, you will have VF and VFG here, right? So likewise, you can use the same set of equations that we use to deal with quality and specific volume to deal with quality and internal energy. So we can use these equations. Are we clear there? Are we clear? Perfect. So now you know, if the quality is given, you can find the specific volume at a given state inside the dome. And if the quality is given, you can find the internal energy of a given state inside the dome. Or else you can go the other way around, right? If you have the state given, the specific volume given inside the dome, you can find the quality. If you have the internal energy given of your state inside the dome, then you can find the quality, right? You can go back and forth. Now we have this example. I want you to try the first one. Substance is water, temperature is 60, pressure is kilopascals, 500 kilopascals. Now find the phase and the information here, right? I want you to take about 4 minutes and work on this one. Has anybody found the answer already? Okay, so which table to use, right? So we always start with saturated water tables, like if the substance is water, so we start with saturated tables. So you can either start with temperature entry or pressure entry depending on what you are interested in. So let's solve it together. Okay, Desa, that's good. Like compressed liquid. Okay, let's see whether it's compressed liquid, right? So I will draw a PV diagram. So you can deal with a TV diagram as well. So either works. So now we have PV diagram, right? So now in this one, what I'm going to do is I'm going to draw an isothermal line. Oops, sorry. An isothermal line for my temperature. So which is 60 Celsius, right? So that is there. Now my pressure is 500 kilopascals. So in order for me to determine the state, what I want to know is the pressure at the saturation point, like saturation pressure, right? So therefore, I go for my temperature entry tables because I started with temperature. Now I need to know my saturation pressure. There, I would type water, and then I go until. Okay, so now I am at saturated water, temperature entry tables, and there I want to find my temperature, which is 60 Celsius, and there I have the saturation pressure 19.94 kilopascals, right? So I go back into my question, and this is going to be 19.94 kilopascals. The pressure is going to be that, right? But my pressure is 500 kilopascals. My pressure is 500 kilopascals. It is 500, right? So obviously it is crossing. My state is here. My state is here in the compressed liquid region. Desa is right. Excellent, right? So now, as I know it is in the compressed liquid region, I will go back into my property tables, and then I will search compressed liquid water. So there in this table, I have 500 kilopascals, right? I have 500 kilopascals. Therefore, I can, therefore I can, sorry, therefore I can pick the properties right away. I need to go to the applicable temperature, which is 60, and there I have all the properties that I need. Specific volume and internal energy. The specific volume is 0.001017, right? So we'll put that one. This is going to be 0.001017, sorry, 17, right? And then internal energy, let's go back. Internal energy is 251.00. It is 251, right? And looking at that, I can find the quality, right? X can be written as V minus Vf divided by Vfg, or oh sorry, quality is not applicable here. Sorry, my bad. This is non-applicable because it is a compressed liquid. I don't know what I was trying to do. For compressed liquids, the quality cannot be defined, right? So the phase is compressed liquid. Now, importantly, let's try to do something else. You remember in the last lecture we emphasized so many times that if we want to find a property in the compressed liquid region, let's say specific volume, we can find, if we don't have that pressure or compressed liquid tables available, we can go to saturated liquid line and we can get the property here, and it would not change too much. It would not change too much from the context if we had a compressed liquid table, right? So how do we know it's compressed liquid again? Okay, uh, so let me explain this one first, Domi, like then I will come back to you, right? And then now we add this, like V equals Vf, right? So let's see whether that assumption, that point we made in the last lecture, is valid. Now to do that, what we can do is we can go to our saturated tables and see it's whether it's valid, right? Sorry, need to go up here. Okay, saturated water, right? We said in such a situation, pressure does not matter. What we are looking for is temperature, and we pick the value for our temperature value, right? So our temperature is 60, and if we want the specific volume at this point, so we were supposed to get Vf, right? Okay, this does not have Vf because this only have enthalpy and entropy, so we scroll up. And this could be an easy confusion, like you might in the exam, if you come up to this point, you only have enthalpy and entropy. Don't panic, it's just up there, right? So Vf and Vft, all our friendly parameters are back, right? Now we pick our temperature 60, and then we look for Vf, which is going to be 0.01017. So if we did not have the compressed liquid table, we would put this value as our 17, right? Now for internal energy, we'll pick the value again. For internal energy, UF, similar to specific volume, we pick UF. It is going to be 251.09. So it is 251.09. Can you see the difference? Can you see a difference? Can you see how close these two parameters are? So it brings us to another important conclusion. So if we do not have compressed liquid tables, or if our compressed liquid tables does not have our given pressure whatsoever, so in that case we can use our saturated liquid property at that given temperature, right? It applies for specific volume and internal energy both. We'll see whether it's true in the coming properties as well, like enthalpy and entropy. But for now, we know that for specific volume, even if you use the compressed liquid tables, or if you use saturated tables and stick to Vf and Uf, you will get the same answers. Am I making sense? Is it clear? Okay. So now, Domi, like, did you get how to figure out the phase sorted out? I think it's all good. Like determining the phase is very important, because like that is something you will be tested strongly in the coming quiz as well, right? So familiarize yourself on how to determine the phase and stuff. So yeah, now the second one. This one, you remember in the last lecture we also had a similar one, either pressure or temperature given, and specific with specific volume, right? In this one we have the pressure and we have internal energy given, right? So as this is different, as this is a little different, I will try to solve it myself rather than asking you to do it, right? So what we can do is we can draw a PU diagram, right? When we draw the dome, you know that this value is going to be UF for that given pressure, This value is going to be UG. So we are here again doing the same thing as what we did last time. What we are trying to do is we are going to compare our U value with UF and UG at 350 kilopascals at the given pressure. If it is temperature, at the given temperature. Now what we have is pressure, right? So as we have been provided with pressure, should we go with, we always start with saturated tables, right? So should we go with pressure or temperature entry? Any suggestions? It's always pressure if the pressure is given, right? It's easy. We have a nice 350 kilopascal pressure. So we look in here, and now what we are having right now is temperature entry tables. So we go down, saturated water, and it's still temperature entry and temperature, and it's everything temperature. Okay, now we have pressure, right? We have 350 kilopascals. Now what we want to try is to find UF and UG, right? So saturated water pressure entry, we have UF and UG. So UF column is this one, and UG column is this one, right? So our temperature is, our pressure is 350. So our UF is 583.93 and UG is 2548, right? So that means, so like UF is going to be, again, sorry, my bad, I forgot it, 583, let's say 583, right? And then our UG is going to be 2548, 2548, right? And what can we say about our internal energy value? Our internal energy value is 1500. Is it inside the range, or is it in the compressed liquid region, or it's in superheated region? What can we say about our current state by looking at UF, UG, and our value? This is liquid plus vapor region, and this is vapor region. Anybody? Our internal energy value is excellent. That is right. Christopher and Stephen, like you are getting it right. Okay, so our UF value is 583, and our internal energy value is higher than our UF. So it is definitely somewhere in this range, right? And then we compare it with our UG value, and UG value is around 2500, which is higher than our value. So definitely our U value is going to be somewhere here, right? So now with that, we know that it is in liquid plus vapor region or two-phase region, right? You can write either, so it's all good. And then to find quality, we can use internal energy, right? X equals U minus UF divided by UFG, right? So using X, we can calculate V equals VF plus X VFG, right? Pretty straightforward, huh? Like, any questions so far? Like, anything not clear about this one, this process? Perfect. So the coming questions of this example will be similar, but look for the substance. It's not always water, because if I go up, so we have two water states, we have ammonia, R410A, and everything, but it doesn't really change a thing, even if it is not the same substance, right? So like this one we solved, and it is same as solving this one, right? because we have temperature and pressure, and how do we determine the phase and everything? It doesn't have anything to do with the substance. We just have to pick the correct tables for that given substance. That's the only thing that we have to be careful when the substance change, right? And I want you to solve these three parts at home, okay? And please make sure that you do it. And once you are trying it, if you encounter any difficulties, bring that to Monday's lecture or your tutorial to your TA. So in both places you will get answers, right? And then I would like to go into a more complicated question that we did not cover from lecture 3. Did any of you complete this one already? Anybody completed? Okay, so okay, let's try to go through this together so that you can get a sense how to interpret the thermodynamic process and how to tackle the complex problem, right? This is not exactly complex. The process is, I mean, understanding the process is key, right? Okay, let's go through the question. A storage tank is filled with methane of 25% quality. So 0.25 is our quality, right? At 120 Kelvin. Okay, the temperature is given in Kelvin, right? So please note that. Due to a system malfunction, the tank temperature increases by 5 Celsius per hour, right? Our initial state is mentioned here. This is where we were at the beginning, and now it says due to a malfunction of the system, the temperature started increasing 5 Celsius per hour. So it is the same as increasing the temperature by 5 Kelvin per hour, right? Because the unit size of Kelvin or unit increment that we see in Kelvin or Celsius, both are the same, right? So either ways increases by 5 Celsius per hour. How long would it take the methane to reach single phase region, right? Okay, now after increasing the temperature, it says that okay, it can reach single phase, and ask how long would it take, right? And if the maximum pressure the tank can withstand is 800 kilopascals, would the tank will operate safely until the substance enters single phase region? Okay, a lot of questions at the same time, but we'll take things slowly, right? So if you look at our PV diagram that is indicated here, you can see our state 1 should be inside the dome, right? That is no argument because we have a quality given, right? And this is a storage tank. Usually storage tanks does not expand unless it's trying to explode, right? So we can assume the volume of the specific volume of the storage tank to be constant. And if the storage tank is not open, like for spillage or whatsoever, if it is a closed tank, it should, I mean, usually storage tanks are closer, right? So it gives that idea. So it's a closed tank. Then the mass is not going to change. Then what can we tell about the specific volume? Is it going to change? Specific volume of the tank, is it going to change even if we heat it or whatsoever? It's not going to change, right? So now that is a relief. Now we know that we have one parameter fixed during this process. Now we locate our initial state, and there it says due to a malfunction, due to a system malfunction, right? We have located our initial state with the black dot, and due to a system malfunction, the temperature rises. So when the temperature increases, like you know that with saturated temperature and pressure, like everything inside the dome is going to be related to each other. Like if the PSAT, I'm sorry, PSAT and TSAT are coming in tandem, and as we go up, the temperature rises, right? when we go this direction. Pressure and temperature both rises. So then we know that as the temperature increases, we go upwards, right? We go upwards. And then it asks the time to cross the liquid plus vapor region and enter a single phase vapor region, right? So once it crosses this point, it enters single phase region. So the question asks, how long would it take for the system to reach single phase region? So to answer that, we need to find how long would it take to travel this distance as a process, right? So a temperature rate is given, so 5 Celsius per hour. So if we know the temperature at this point, T2 and T1, the time taken to travel this distance can be given by delta T divided by the rate of temperature increment. Are we all in agreement up to that point? Can we confirm in the chat? Okay. Now, there's another important thing to note. Before that, we'll try to tackle the information that we know already, right? So depending on this information given, we calculate V1. V1 is equal to Vf plus X Vfg because it's inside the dome and we know the quality. And what we want to find is Vf and Vfg, right? So important to note, this is given in Kelvin, 120 K. So check the units of your tables before you jump into values. So what is the value? Material or substance? Methane. So I will type methane and search for methane. Now we are at methane. Now it's important to note, in water tables, the temperatures were given in Celsius, but here it is given in Kelvin, right? It is given in Kelvin. So what we are interested in, 120 Kelvin, right? 120, was it 120? Yes, it is 120. And from 120 Kelvin, we can go here. And then we have all the properties we need. What we needed was Vf, Vfg, and Vg, right? So we bring that up here. And now we have Vf and Vfg. So we can nail down the specific volume at state 1. Are we clear about that one? Are we clear about that one? Okay, so this is just using the property tables to calculate the initial state, or to find the properties at the initial state, right? So up to that point, it's what we have already done. Now, in order to find the point at which we cross the boundary, we need to find this point, right? So at this point, what is the specialty of this point? Do you see that at this point, the Vg at Vg2, right? Let's say the saturated gas point, or Vg2 at state 2 is equal to V1. Do we agree with that one? Because our specific volume did not change, and when we are at the saturated vapor line, then it should be Vg2, and Vg should be equal to our initial specific volume. Do you agree with that? Perfect. But there's a catch here. First, we need to check whether we want to write Vg2 equals V1 or F2 equals V1, because if let's say our critical point is here, critical. If point 2 is to the right of the critical point, then what can we say about the line that it is on? Is it saturated vapor line or saturated liquid line? Any ideas? It is saturated vapor line. If it was to the left of critical point, is it saturated vapor line or saturated liquid line? It is going to be liquid line, right? So if it was referring to this line, we should be using this relationship, right? The second relationship in red. And if it was to the right, we should be using the one in blue. Do we all agree with that? Critical point does not stay in two-phase region. It is on the top of the dome. It is not inside the two-phase region. Okay, so do you agree with the argument like we are discussing right now, or anybody who's not clear about this one? Okay, so the question is, if our state is to the left from the critical point, then it meets the saturated liquid line as we heat, right? So therefore, in such a situation, we can say this red relationship stays. And if our state 1 was to the right from the critical point, then as we heat, our state meets the vapor line, saturated vapor line, and there this blue relationship stands. Do you all agree with that? Anybody having doubts? Anybody having doubts? Okay, perfect. Now, in order for us to know which relationship to use, first we need to know whether our V1, whether our V1 is greater than V critical or less than V critical, right? So that is a requirement now. So we go into property tables and go to critical. We search critical, we search critical and then go there. Okay, so we come to critical constants and our substance is methane. So we go to methane. So methane is here and the critical volume is in the last column, right? Sorry, critical volume is in the last column, V critical, right? So therefore we'll go to our substance of interest, methane, and we'll pick the value in the last column, 0.00615. We bring that in, right? Critical volume is 0.00615. Okay, so now this is V critical is 0.00615 cubic meters per kilogram. right? And our specific volume is given here to be 0.078, right? Which is greater than VC. When it is greater than VC, where does our state 1 fall? Like, is it to the right of VC or is it to the left of VC? What can you say? Anybody? Right or left from VC? It falls to the right, because VC is the x-axis. Then 0.078 is higher than 0.00615. Therefore, we can see that what we have drawn here is correct, the process, right? And therefore, we can see that we don't have to worry about meeting the saturated liquid line at this particular instance. So this relationship does not matter anymore. Now we don't need this relationship because our interested point is doing something else. Okay, now we are good to go with the blue relationship, right? This one. Okay, are we clear up to that point? So x-axis the specific volume, x-axis has the specific volume, VC is 0.00615. The specific volume we have is 0.078, which is greater than VC, so it should be to the right of VC. Am I making sense? Okay, so now we have to find a saturated vapor with this given specific volume, right? So as we are looking at the saturated vapor line, we have to look into the VG column of the property tables and have to find where we can have this specific volume, right? So our substance of interest is methane. So now we'll go to property tables. We'll go to property tables and find methane. Thermodynamic properties of methane. So we are right here. And then we want to find our specific volume, which is 0.0783, right? We look for 0.083 in which column? VG column, because we are interested in what's happening on saturated vapor line, right? 0.07. 0.07. Okay, let me zoom this one in a little. This is the column that we are interested in, and there 0.077 is here, right? And we don't have the exact number as 0.078, right? If we want to make it accurate, we can always interpolate to find the exact temperature. But at this point, I will assume this one is the number and this is close enough for me. So I will pick 145 Kelvin. But if you feel you need to get further accuracy, then you have to find the bracket in which the 0.078 is included. So if you go down to 150, your specific volume is 0.06, which does not include 0.078. So if you go up here, 0.078 should be somewhere between these two numbers. So if you are interested in doing interpolation, you have to pick 145 and 140 Kelvin numbers here, and these two specific volumes, and then do the interpolation as necessary. But for now, like, as this is significantly close, I am picking this number only. So now we have our temperature when we cross the specific vapor saturated vapor line as 145 Kelvin. Do I make sense? Anything not clear up to this point? How do we arrive at 145 Kelvin or anything? So PV graph will not be given. PV graph, the shape of the PV graph, TV graph, and PT graphs you should remember, right? So V equals VG. Yeah. So V equals VG happened as we had a constant specific volume. It's a rigid container and constant mass. So specific volume does not change as the phase goes by, as the process goes by, and we keep on heating until we meet the saturated vapor line, to see when we cross the boundary. It's true that Vg is always on the saturated vapor line. So let me, okay, Alan, you're good? Okay. So Minna has a question. I do not see 0.077. Yeah, you do not see 0.077, but you see 0.078, right? So we had let me draw a table. We had few things here. 0.077 here, and it was 145 Kelvin. This is temperature, this is a specific volume Vg, and then we had 140, sorry, we had specific volume as 0.09841, and our specific volume that we are interested in is this one, right? And so this one, and we need to find the temperature at this point, right? So what I did was I assumed that 0.078 is significantly close to 0.077. So that's what I did, right? So that's why we have 145 Kelvin. So if you want further accuracy, then you can interpolate it between this bracket and find the temperature, right? So interpolate, like if you find similar questions in the exam, to avoid any errors, I would recommend you to do interpolation all the time. So that way you will be in the safe region, right? So if you are not sure like how much error that's going to create, then it's always recommended to like interpolate. So I did not interpolate because that's another step just to explain the process, right? Do it make sense? Okay. So now we need to find the time taken to cross the boundary. So what we need is, like, we have been provided with a temperature increment rate. So if we know the temperature difference at point 1 and point 2, then we can do the calculation, right? So 145 we found already, 120 given, so that is the temperature difference. And if 5 Celsius temperature difference happen every hour, we can find how much time taken to complete this given temperature difference. So some of you might be wondering, okay, the temperature is given in Kelvin, but the temperature rate is given in Celsius, but it does not matter, as I explained at the beginning. So Kelvin and the Celsius difference is going to be the same. So let me quickly write it down here. Let me erase some of this information. Okay. So Tk is equal to Tc plus 273, but delta Tk is equal to delta Tc, because the 273 portion, 273.15, that portion is a constant. So if you have T1 and T2, when you subtract these two, 273 is going to cancel out, right? So that's why we can use this relationship, even though these are in Kelvin and Celsius. So your answer will be 5 hours for that question, right? Thomas, we'll have to memorize interpolation formula. Please check the formula sheet in the modules, like under important documents. If the formula sheet does not have it, then you have memorize how to do it, right? Anything given in the formula sheet can be used during the exam, okay? Or else you have to memorize it. Yeah. So delta T, everybody understand how we came across this delta T value? Okay. Now, then the question asks another thing. If the maximum pressure the tank can withstand is 800 kilopascals, would the tank will operate safely until the substance enter the single phase region? Okay. So if 800, let's try to find the pressure at saturation point, right? At state 2. Let's get that pressure real quick. We found that state already, 145, and at that point the pressure is 823 kilopascals. So now this is 823 kilopascals, right? Do we agree with that? Like, anybody have confusions how we arrive at the pressure of this point? All clear? Okay. Now it asks, if the maximum pressure the tank can withstand is 800 kilopascals, would the tank will operate safely until the substance enter the single phase region? What can you say? Would it be safely arriving at that point? Yes or no? Would the tank explode or not before arriving at single phase? Explode, yes. That is correct, because 800 is below 823 kilopascal, right? So we arrive at the maximum capacity of the tank before we reach the single phase region. Therefore, the tank won't make it to the single phase region, rather it will explode, right? Are we all clear? Perfect. So do we have any questions regarding this problem? Anything not clear? Any issues? It explodes because its maximum, the maximum pressure it can handle is 800, and the pressure at saturation vapor line is 823. So the question asks whether it would be able to safely arrive at
the single phase region? No, because the maximum pressure it can handle is being exceeded when we try to cross the line, right? So if we get this on the exam, will we always be constant on the question? No, like we always constant is not a thing. Like, so if you solve the assignment questions, you'll see you have to see the physical system. If the system, like if it is a storage tank, it does not change the volume, right? So if there's a piston cylinder mechanism, there's potential that it change the volume. So, and obviously this question itself, like this, I won't give it in the exam, right? Are we clear? Mena, did I answer your question? Awesome. And can you explain again how you got 823? Yes, because we found this state earlier, right? So it is how we arrived at 145 Kelvin. So this is the state. So I just went to the property tables, and at the state, what is the saturation pressure? So that is what I picked right now. Okay. So in a tank, in a rigid tank, it does not change. No. Unless there's a mass inflow, right? Or mass leakage or something like that. Okay. So any further questions? Okay. So this one is using the ideal gas law. So I just wanted to show you how to solve this one. It's pretty straightforward. An IC engine aspirates 0.1 cubic meter air volume at 227 and 1000 kilopascal, and after the constant volume combustion process it reaches 800 Kelvin. Find the mass of air and final pressure of the process. So this one is to demonstrate how to use the ideal gas equation with air. So to find the mass, pressure and volume given, and the gas constant, you can find this from the property tables, and temperature is given to be 227 Celsius, and important, 227 Celsius cannot be substituted here, it has to be converted to Kelvin, right? So with Kelvin we substitute that and we arrive at the mass. So that was a pretty quick explanation, less than 30 seconds, but is there any questions regarding how we arrive at mass? Not Mars, but like the mass of the system. Anybody having doubts? Anybody who's clear? Or anybody who does not understand what's going on, because we entered into this new question, right? That's what happened. So now it says after a constant volume combustion process, right, it reaches 800 Kelvin. So constant volume. So again, the volume does not change in this question as well. So you have to look for the clues. It says constant volume. So it is a vertical line going upwards, right? Now we are supposed to find the final pressure, right? So when we apply the ideal gas equation to state 1, it's going to be P1V1 equals MRT1. And when we apply the ideal gas equation to state 2, it's going to be P2V2 equals MRT2. Right? So we divide the equation 1 by equation 2. No, not divide the equation 1 by equation 2, sorry, my bad. So we can do that as well, but rather than doing it, so we can get an expression for M, right? So M of the system, mass of the system does not change inside the system, right? So therefore, we can say that M1, this is the expression for M1, this is the expression for M2, right? and m1 equals m2 because the mass did not change, and the constant just cancels out as it is in both sides. And then this is a constant volume process, and v1 just cancel out, and then we arrive at p1 over t1 equals p2 over t2, and then from this equation we can calculate p2, p1 known, t2 and t1 known, so we arrive at the answer.